Okay, let's start this last session on grids. Before starting the session, let me remind you to fill the feedback form. The organizing committee asked us to remind you to fill the feedback form, which is online. And then let me introduce the first speaker, which is Mathieu Goutel from UREC, CNRS France. And he is working on behavior of TCP over a DiffServ-enabled gigabit network, and he will talk us about network activities in the EG project. I'll warn you 5 minutes before the end of the talk.
So, could you hear me? Yes? Okay, so good evening, everybody. So, as Roberto Barbera says, I'm Mathieu Goutel. I'm working currently in the SA2 activity of the EG project, and I will present you the networking activities in this project. So first a few words about the EG project. So the EG project is a 2-year project. The aim of this project is to propose the scientific community a grid infrastructure, more or less round the clock. Currently, it federates the national and the regional grids in a global infrastructure. New middleware is currently being released, which is called G-Lite, and many applications are foreseen to run on this infrastructure. What we have between the core of this infrastructure is essentially the network, just because without the network the grid doesn't exist. So just to show you what is the current status of EG grid. So there is mainly sites in Europe and around the world. So in Asia and some in the United States and South America. So it's about more than 130 sites and many figures, about 12,000 CPUs and more than about 5 petabytes of storage. So inside this project, we have two network activities. The first one I am involved in is the SA2 activities, so network resource provision. There are 3 main tasks. The first one is to have an interface between the EG project and all the NRNs and all the network communities. This interface is called the Technical Network Liaison Committee. This is a group which meets every 6 months to discuss about technical problems, new issues, to present the models and the work that has been done in both the EG project and the network communities. The second task is to build an operational interface between the grid and the network user support, and also to try to create SLAs between the EG and the network in order for the application to use the network services provided by the network. The second activities is about network service development. There is 2 network services that are being developed. First one is about network performance monitoring, and the second one is about bandwidth allocation and reservation. There is also a small activity about IPv6. I won't tell so much about, just because it's more an activities to bring the application some kind of IPv6 awareness and to try to push the developers and the seed administrator to try to think about IPv6. It's not about an IPv6 deployment inside the whole architecture. So we try in all these activities to build working relationship between grid and the network providers. So mainly giant and NRNs. Our approach is to try to. Sorry, can I? So it's try to push the network as a class of grid resources, just like computer and storage elements. So it means that we need to introduce in all the grid architecture some kind of network resource provisioning mechanisms. The big problem is that this spans far beyond the control of a normal grid project. The network is not under the responsibilities of the grid world, and it depends essentially on the network services network providers are giving us. So currently, the only service which is implemented in most of the networks in Europe is Premium IP. And even this service is not available in all the NRNs. So what we need is to anticipate on the services GN2 is currently developing. And a problem for us is that GN2 is a long-term project. It's 4 year, 5 year. And we are in the EG project, a 2-year project, which started 6 months earlier than GN2. So there are a problem just because they are in the definition process, and we need on the EG side to provide something to the application. So there is a clash between these two timelines. So we try to work on a long-term perspective and try to build something strong to introduce the foreseen network services as quick as possible. Okay, sorry. Sorry. Okay. So, no. It's more complicated. Yes, sorry. So about the network, the network operational interface, we try to define the interaction between the grid user support, so the grid users and all the seed administrator, and the NRN NOCs. So it mainly deals about SLA management and the trouble tickets exchange between the two systems. So we try to define the procedures and the flows between EG and the NOCs. It is really important for us just because if we want to have an operational architecture and a resource which can be accessible around the clock for scientists, we need to have this kind of operational mechanisms to try to troubleshoot problems. It will, of course, not replace the current interactions between the seat administrators and their NRNs or their regional networks, of course. It is just to try to exchange information between the two supports. So we have to face many problems. for example, about tickets. A simple one. Tickets, for example, in the Greek NRNs are written in Greek. And if we want to import it in a global grid user support, as it exists today, we have to translate it. But there is no formal templates for all the NRNs in the Europe. So we have to develop a tool which can translate most of the NRN's ticketing systems in the one we are using in EG. So there is mainly two information flows in the operational interface. So first, when a ticket comes from Giant or NRNs, it is handled by a team inside EG, which does some kind of filtering to see if the ticket or the incident has an impact on the EG network. So if, for example, it breaks a link between two sites, and if it has some relation with an EG network, it creates a ticket in the grid user support to inform the users. On the other way, if a user detects problems, for example, he cannot reach particular sites, he creates a ticket in the trouble ticket manager, the global grid user support. Then a team, the ticket is assigned to a particular team, and this team will deal with the NOC to try to troubleshoot the problems. About SLAs. We have based our work on previous work done in previous projects, and we have worked with GN2 to try to define SLA templates and to try to have some kind of end-to-end SLA. For the moment, we can imagine that there is SLAs in each of the cross network between two EG resource centers, and from these three SLAs in the picture I show you, we can combine them and try to build border-to-border SLAs. So from the ingress of the first NRNs to the egress of the last NRN. We try to accommodate with the last mile, so try to have SLAs with campus network or regional network, and then we will try to build end-to-end SLAs. So scenarios can be the one I will explain. So we have categorized every networks. It can be in. We have identified three categories. So if it is compliant, supportive, or indifferent to the service we want to address. So I take as an example the premium IP service, as it is the one which is currently more or less available, but it can accommodate with many network services, and it is not dedicated to this kind of a service. But for example, if we have along the path between two resource centers, all the networks are premium IP compliant. So it means that they implement the premium IP service, and they can give us back some monitoring figures about the service they provide us. It's okay. We can build the end-to-end SLAs, and we will provide a service to the application for example, a real-time stream or real-time interaction. If there is what we call premium IP supportive domains, it can be, for example, a network which is over provision, and if he can ensure us that his networks can provide us a service which is, from the application point of view, more or less the same as a premium IP service, and it provides us monitoring infrastructure, it is okay. It is still okay. We will have maybe not so good service as in the previous case, but still okay from the application point of view. The problem comes when we have some PIP in different domains. So it can be that a network doesn't provide any services, is not over-provisioned, or it can be, for example, another provision network, but which doesn't provide any monitoring infrastructure. So in this case, we can't provide end-to-end SLAs, so the applications can't rely on some guarantees. So in this case, we cannot build the end-to-end SLAs. All these installations of SLAs and monitoring and all the procedures we have defined, we will try to implement them in QRS experiments. So this is not a network test for premium IP. This has already been done. We don't want to reinvent the wheel. So what we want to try is to validate our procedures. So we want to have a better knowledge of SLA processings and try to see how the applications can require these network services and try to identify some issues about the procedure we have defined. So what we are trying to do is to use the network services between two resource centers crossing three different domains. So for the moment, we identify the flows with the DSCP, so a special DSCP values. And the first router will remark the packets. This kind of mechanism allows us to identify many applications, and even if they use the same network services. So in this case, the premium IP service. We can identify application with many mechanisms, for example, TCP port or whatever, but we try to choose we choose the DSCP value just because it's simpler for us to tweak this kind of marking. So here we are. So I presented you the EC2 network resource provision, and I will switch now to the network service development. Okay, so sorry. So GRA4. So there is the GRA4 approach is to provide clients some kind of seamless mechanisms to access monitoring figures. So they choose the NMWG interface. So this is a standard interface which is developed inside the GGF. And all these monitoring figures can be used by site administrators for monitoring SLAs, and also to choose a particular sites to decide a particular source for data transfer. So there is a prototype ready. There was a demo during the last GGF. They are currently working on security, and now they want to push the use of their monitoring figures inside the middleware to do the matchmaking of sites and to choose, for example, a particular storage element to do the transfer. So to give you a better idea of what we are doing, currently there is a lot of monitoring architecture. So providing that they all publish their data through an NMWG interface. It may be not the case, but in this case, you have as many clients as a monitoring framework. So if all the framework publish their data through an NMWG interface, your clients can access all the monitoring infrastructure. What GRF4 is proposing is to have some kind of layer in between, which still publish data through an NMWG interface and access all the framework using their interface. So in this case, you can have one single diagnostic client, which can be the middleware, a site administrator, a monitoring website, whatever you want, and it accesses this mediator to have access to delay monitoring or whatever you want. The work of GRF4 is not about developing another monitoring framework. There is so many that it will be useless. So they just want to publish all the data gathered in the existing framework. About BAR, it's more or less the same about BAR. It is just an interface for the grid users, so the grid middleware, the applications, to use a particular network services and to access what is provided by the network. So if it needs a strong participation of NRNs, if I show you the architecture, people who were in a talk on Monday have already seen this picture. You have the high-layer middleware in yellow, the bar component, which talk to what we call a network service access point, which will deal with all the configurations in the network and do the true reservation inside the core network. BAR will never access a particular network routers. If we want to deal with the last mile problem, we have to add a local network service access point, for example, to configure the campus network or the regional networks. It can accommodate with this kind of situation. The reservation architecture, it was presented yesterday by Tiziana Ferrari in its talk. I will just say a few words that we want to integrate the network resources in this reservation architecture. So it may deal with storage, computing resource, and network resource. So we try to work with Géant2 and to can use their network as soon as they will be available. So the conclusions, I think that networking people has to consider the grid only as a particular user, as one of users, maybe big, maybe federated. It is not a problem, it is not an issue. It is just a user which wants to use their service. And I think that a network has to provide their customers, their user, some mechanisms to use their service. In terms of SLAs, we want to push our model, but NRNs can just reject it. And these kind of issues, SLAs are very new from our point of view for grid users and for NRNs. So I think it's very challenging. The operational interface is very important for us to have a reliable architecture. And what we see for the moment is that we need more steps to try to fulfill the requirements of application. It is not the case for the moment. Again, I want to stress that we have good working relations with NRNs and JN2, and this is very promising for the future. So thank you. If you have any questions.
So the floor is now open for comments or questions. One over there.
So the thing that bothered me quite a lot is the middleware people in general, and this certainly includes, the G-Lite people who I know, right, really don't want to know about the network at all. But, they just assume it's there and the sockets work. But how do you manage to make them make efficient use of the network when they refuse even to have a model in their middleware for what might be a good or a bad way to use the network?
That's exactly what we are there. We are more or less networking people inside a grid project. So we want to abstract them the network, but in an efficient way. So this is exactly why we want to participate to the definitions of reservation architecture inside the middleware. Just because when we first read their definition document about reservation, we find it in a state that it cannot work with the network, and we try to discuss inside the network activities of EG and try to propose them some things which can accommodate with both views. It means that we propose them mechanisms to use the network services in an efficient way without changing so much their view of this network black box. And this is, I think, this is why we are there, to try to not change their mind, but use the network in the correct way.
Thanks. Are there any other questions or comments? Okay. If not, let's thank the speaker again. And move on with the agenda. The second speaker is Mazuma Zan, Senior Technical Leader at Cisco System, and he will give a presentation on factoring lower networking layers into the grid. I'll warn you 5 minutes before.
Okay. Try this one.
This one. Do you know how can we set on full screen? No, I mean just do like a presentation. You have this feature. If not, I mean, you can go ahead. Yeah. We can leave like that. Okay.
Yeah. Okay. Can you hear me? The topic of my talk today is the factoring lower network layers into the grid. When I say lower network layers, are as basically layer 1, 2, and 3. This is joint work with Wayne Clark, Monique Morrow, who is here, and Malik Tatipapunga. Let me start with the agenda. First I want to talk about a little prologue on the various grid communities that we have who are involved in grid-related activities, basically grid network users, owners, administrators, providers. Just want to talk about that. The reason that I want to talk about that because depending on which community you are talking about grid, the concept may differ. Then, a little bit on the typical grid domain, which basically they are layer 7 resources. Already mentioned about that. Basically, the layer 7 resources are first-class grid resources. I want to talk about that a little bit. Then, how do we factor what I call non-first-class lower layer resources into grid? And talk about why not first class and why factor in. Then get into what are the resources that we have to factor in. One is the performance cost metric resources, another is the service and capability related resources. Then I'll go over a few use cases. One of them is network aware job distribution, job scheduling, network aware job distribution based on LAN resources, a little bit on the grid VPN concept, and then I thought that we'll throw in some concept on grid control plane, quote unquote control plane, and grid quote unquote routing. We are definitely not covering security and multi-provider issues. Definitely, there are a lot of other things that we are not covering in here. So first on the grid community, right? So so starting with this classification, the reason is that as I said, that concepts and features may differ depending on who is investigating and who is deploying or working on the grid concepts. We classify the grid community into two major areas or divisions. One is the commercial one, because the grid community mostly focused towards the research. Basically, the research community are involved mostly. Now, grid also is slowly getting traction into the commercial domain. So in the commercial domain means the enterprise IT, for example, that manages a network and serve various departments. Let's say that, for example, a pharmaceutical company getting into grid, or even an enterprise that runs an application like SAP application, for example. And SAP, for example, is gridifying their applications, and financial house or enterprises, they are using those gridified applications. Then you may have also consortium of grid enterprises. I think EGE probably is one of them, but more on the research side. Then we have the commercial service providers, right? Like British Telecom or AT&T or SBC, those kind of big commercial service providers. It's a totally different domain from NRN. Then we have the non-commercial or not so commercial domain, which is the NRN, National Research Network Service Providers. And you can classify the NRNs also into kind of two different islands. Like one is the production NRN, another is the research NRN, right? And then you have the research community, university and research labs and things like that. So now, as I said, we all know that typical grid domain deals with the layer 7 resources. Basically, the layer 7 resources as the first class grid resources. So grid applications or grid middleware, they deal with computers, servers, clusters, supercomputers, and storage, right? So first-class resources mean that those are the resources that those middleware or application or tools, whatever grid tools are there, they manage. Ideally, you can basically consider the whole network layer, ISO-ISI layer, like layer 2, layer 1 to layer 7 as, first-class grid resources. There are some researchers who actually are kind of working in those areas, like where, everything is grid resource. I have seen sitting in a number of grid sessions, and folks did talk about network as a resource, but they did not spell out, what does that exactly means, right? So, if I have a router, is it a grid resource? Yeah, could be, but it depends also which community that grid is being used or applied to, right? So now layer 1 to layer 7, all the resources that grid resource probably is okay in the non-commercial space, or maybe in the research NRN, like Lambda grid, but may not be suitable in the commercial domain. So why? Consider, this grid application or grid middleware that serve grid applications, or consider the grid middleware component like a scheduler. So take a scheduler or take any application. So should you, or take any kind of tool, grid tool, should, in the commercial space especially, are you going to allow those tools to configure routing protocols, or configure or tweak the let's say WSPA parameters? I don't think that's a good idea, especially in the commercial domain. So you have to have some sort of layer separation and administrator control separation, which is very much in effect in various commercial domain. Even if let's take a commercial service provider like BT or AT&T, even if it is one single organization, like one autonomous system in IP term, they have different administrative domains. Like their transport network is managed by one group, their IP network is managed by another group, and things like that. So even they have, their separate islands of administrative control there. So, the grid layer, especially the layer 7 grid layer, grid middleware, and the network management layer, for example, cannot be in the same administrative domain. Then basically you should also separate the grid middleware somehow from the underlying networking technology. So whenever underlying networking technology changes, it should not affect the middleware layer. So it's kind of layer separation. Then definitely commercial network owner, they don't want to get full control of the lower layer resources, may not want to give full control to grid systems. So, but somehow we have to, factor the lower layer network resources into grid. And the factoring basically will involve factoring some limited resources into the grid. And I'm going to talk about, what are those limited resources could be. So, but you want to factor in because you want to do some sort of, the grid middleware or applications or tools, they want to do some sort of network-aware middleware functions. For example, if you want to do network-aware global job scheduling, yes, you have to factor in somehow the lower layer resources into the grid. You may also want to factor lower layer resources into the grid if you want to do indirect provisioning of resources on demand or as needed basis. But I'm saying here, you see, those are highlighted in red, that indirect, meaning that you are not going to, in the commercial space, not going to allow grid middleware to directly go and provision the network, tweak the OSPA parameter, and set up the tunnel and tweak the parameters there. I don't think that's, especially in the commercial space, that will be the case. So basically, so this is what basically factoring in means. So if we look at from a middleware perspective, it's a very high level, kind of architecture. There on the left-hand side, you see the middleware. So on the lower part, you see that we have already the layer 7 resources factored in by middleware. But somehow also we have to factor in the layer 1 to 3 also into the middleware, right? So then we have to put a layer somewhere here is a kind of abstraction layer between the middleware, grid middleware layer and the network provisioning or the network layer, right? Lower layer network. So that's the basic idea. So and what are these resources could be? These are abstract resources. Could be performance and cost related, but those are network based. I'm going to talk about that, what does network based or initiated performance cost metrics means, because they do differ from the end system or host based performance cost metrics, and some limited service and capability device or network capability related resources that you have to factor in. So first the performance cost metric resources. So first of all, as I said, that these metrics are router or switch based. That means you monitor your monitoring operations. The monitoring operations from which the metrics are derived are initiated from within the network or from within routers or switches. So now contrast this with the typical grid monitoring systems that are host or end system based, right? Or contrast this with the layer 7 or layer 4 performance tuning that a lot of people are working on for high bandwidth delay products, like Wave 100 TCP parameter tuning. Then we have grid FTP, we have high speed TCP, and other UDP based solution and things like that. Now, those solutions, that host and end system based monitoring solution, they cannot actually make use of various features that are available in network-based monitoring for monitoring accuracy. I will give some example in the next slide. So, some example of network-based monitoring quote-unquote tools is the Cisco IPSLA that supports router-initiated monitoring, and it supports various monitoring capabilities or metrics that are network-oriented. For example, MPLS, VPN, BRF aware, the RTT, for example, which you cannot do from an end system, right? You can even do TCP and HTTP connect RTT from a router to an end system. Then we have the NetFlow, for example, which is again a router based. It gives certain information that otherwise you cannot get from end system. Then let's take MPLS OAM that Monique is very much involved in IETF work on that. There also again, ICMP ping is not enough there, because the point is that you have to monitor actually the MPLS LSP data plane, which you cannot do from an end system. And also, for example, the MPLS LSP ping, it supports something called ECMP, which is equal cost multipath or tree trace, that you basically use for monitoring accuracy. And then we also have BCCB for C-dual monitoring. So these are all network based, not end system based. So basically, what we want to do, we want to just put a wrapper on top of this and then expose that to the grid middleware. Then, various network service and capability related resources we have, like, as I said, that the router or a line card is not a grid resource, right? So rather, the network services that are being provided by a network or a router could be grid resource, but not all of them, right? VPN service, for example, you could you could, let's say, take Globus, the Globus middleware MDS. You could basically advertise to MDS, okay, here I have a router that is connected to this grid side and it supports MPLS VPN. So you can go and join to a MPLS VPN if you want to go via that router, right? So that kind of very high level service capabilities, service related capabilities you can expose to the grid middleware layer. Then the bandwidth related, yeah, it's obvious. QoS related, you could have something like, okay, this particular router actually, or this particular network supports something called diverse routing, meaning that, you have to follow certain route, basically certain limitation on the route. Then, VLAN related information, network security also, but network-based security. For example, you can do SSL acceleration on a Cisco Catalyst switch, and if you want to have a path through that, you can basically advertise that to the grid middleware. Then, there are certain kind of device capabilities like jumbo Ethernet frame, which is a kind of requirement for grid, which is a 9,000 byte frame. Supported by Cisco 5K and 6K switches, that kind of capabilities also can be exposed to the capability information can be exposed to the grid middleware. So, as I said, that you expose limited resources, but not the full resource in here. So just few use cases here. For example, you have a job grab workflow. For job distribution, you have jobs like J1 and J2. They do a lot of computation and then they exchange a lot of data between them. Actually, before they are scheduled J1 and J2, they have to load it with a lot of data, and this happens over the network. And then J1 and J2 rise to another job called J3, and which rise to a storage, and then from there you're streaming for visualization. J4 is the application for that. So you may have various kind of requirements like layer 7 requirements, which is the CPU memory related, and then layer 1, 2, and 3 related, which is bandwidth and network QoS related requirements. So when you have lower layer requirements, upper layer requirements, somehow you have to combine them and do job scheduling, for example. Here, this is a example with, various sites, and then you have a metropolitan area network and wide area network in between, and then you should be able to use the information layer 1 to 3 information, the grid resource information to basically perform network-aware job distribution, right? If you don't have that information, you cannot do network-aware job distribution. For example, here we're showing that somehow the grid middleware knows that there is a QoS path between two sites. So if I have to distribute the job, I might use those two sites, right? So, but the middleware does not go on provision. If there is a need for provisioning of resources, the underlying system, like a network management system, will do that automatically for the upper grid middleware. Then, another example how you can basically expose high-level LAN resources to grid middleware and then make use of that for doing various things like job distribution, for example. Let's say that that somehow you have exposed information that I have these and these VLANs, right? And then there are some limitation that certain application in one VLAN you cannot run in another VLAN. Then you cannot go and distribute jobs, for example. Let's say one VLAN is running ERP application, another running engineering application. And you cannot actually, now you have resources available in the ERP VLAN, you cannot schedule engineering job in the ERP VLAN, things like that. Similarly, if you have information about okay, I have a path that provides Jumbo Ethernet, MTU, then I can take that. Then grid VPN. Let's say that you have a MPLS network, and as I said before, that you expose information about the MPLS VPN capabilities of a particular router, then grid sites basically can go and join VPN for, let's say, secure data grid VPN. And all the needed provisioning will be done by the system automatically. I mean, take MPLS VPN. Provisioning of MPLS VPN is very complex. So a grid middleware is not supposed to do anything on that. So underlying system is supposed to do that. Now, okay, so that's more of a using existing systems and creating basically an abstract layer and providing those abstract resources to the grid middleware so that grid middleware can perform network-aware middleware functions like job distribution. Now here is a more of a kind of research topic. For example, we could basically define some sort of grid control plane. Like in the typical case, let's say that you have the Globus middleware and you have the MDS, the directory service, which could be hierarchical, but it's mostly central. So you could have actually a kind of control plane where you could do routing of scheduling requests to various sites in the network. Stable, but this control plane is not an IP control plane or anything. It's an overlay control plane. Could reside in a grid middleware. So we could do that. I think that's it.
Thank you very much. Are there questions or comments to the second speaker? Okay. Okay, so let's thank the speaker again. And let's move on to the last presentation of this section that will be done by Rafal Nikolajczyk from HPC, from the Poznan Supercomputing Center, and they will talk us about checkpoint or restart packages originating in PSNC.
Welcome. My name is Rafał Nikolajczyk, and I'm working in Poznań Supercomputing and Networking Center. I'm working in supercomputing department, and I'm a member of checkpointing research team. Until now, we have developed three packages, three checkpointing packages. One for Silicon Graphics ProPack and two for Solaris OS. And now we are working on grid checkpointing architecture. There is a few layers where checkpointing may be placed. It is the application layer, this is the user layer, and the kernel layer. The application layer is dedicated for aware users because it requires a lot of work to implement its own application, which includes our functionality required to store the application's image. More useful and more simple to use for user is user-level checkpointing, but it has disadvantages. It requires from user to have the source code of his applications. Another checkpointing level is the kernel level checkpointing, which is most advanced, which has most advanced functionality. It is typically integrated with the operating system, and the user do not need to change his application. He just simply used the functions, the commands provided with the operating system. Because the grids becomes more popular, it is the need to make checkpointing technology available in distributed environment. So typically on the grid you run applications which use MPI libraries, and it must be prepared checkpointing which close the communications channels, for example, before storing the application image. There is defined user application interface by global. There is defined user-level application interface by GGF, which allow us to prepare application which will support perform checkpointing. Another interesting issue is the heterogeneous checkpointing, which allow to migrate the job images between different architectures. We have started our developing on Solaris platform in year 2001. Progress project was co-founded by Polish State Committee for Science and Research. We worked on UltraSpark 64-bit family processors. We have developed two packages. One as a user level checkpointing and second as system kernel level checkpointing. Developing kernel level checkpointing was a grand challenge for us because we have developed it from the scratch. Both packages was developed in 18 months. Originally, checkpointing library was developed by James Clark from University of the Tennessee. We have taken the core technology from this library, and we have do some alternations and extensions for this library. This library is designed for applications written in C, and there are only few changes required in the source code of your application. You must modify the main functions and replace the string main with CKPT target string, and additionally you must recompile the application with some parameters. We have decided to extend the original library with the support for multiprocess application. What we have made the assumptions that the application must follow the one parent, many children model. So the parent cannot be the grandfather. This is the flat two-level tree of the processes. Additionally, we have decided that child process may use exec function, so each child may execute another binaries. We have implemented the mechanism for correct handling of wait function. This is important where the child process becomes the zombie process, and during the restoration phase we emulate the zombie processes. We have do Another important improvement, we save and restore memory segments used by shared library, because almost all computational applications use some shared libraries. When you run multi-process application, you usually use some inter-process communication. So we have we must support the ability to save and restore IPC mechanism. We are supporting system file semaphores, shared memories, and message queues. Finally, we have added some less important improvements like saving and restoring signal dispositions, saving and restoring pending signal, signal mask, and we have extended support for open files. Now we can restore the content of the open file. To virtualize operating system resources, you have to intercept some system calls. It is important to know what is the state of the kernel objects which we have to restore during resume phase. If you want to use our library, you have to notice that your application must follow the one parent many children model, and all children need to finish their computation before parent process finished. You have to change, as I mentioned before, main string with CKPT target name, and you must remember that some system calls are forbidden. For example, system calls connected with network activity, with explicitly mapped files, and so on. As you see, it's a simple operation to port your application to our library. You start your application in a standard way. To make a checkpoint, you can use our shell script on. You just simply send the signal sig freeze to the application. To restart the application, you use the original binaries with recover parameter. We have also introduced some configuration method. You can configure some options during execution phase or before compilation. Now I will describe you our kernel checkpointing module. Because it was developed from the scratch, we have made the following assumptions. The user must simply use our package. He should not do any changes in the code of his application. There should be no need for recompiling, linking this application, and there should be no assumptions on programming language, compiler, on libraries. We have decided to write our package as a kernel module, because we have no access to the Solaris source code, and the use of loadable kernel modules is easiest for the users. We are supporting both 64 and 32-bit application, and we wanted to do minimal impact on the operating systems. The core functionality of our tool requires to store basic process information like process memory segments, shared library segments, all process registers, and there are some additional information like information about signals, pending signals, signals mask, signals dispositions. It's also, of course, required to store information about open files used by application. We can store regular files, directories, and partially special files. We are storing the content of open files and actual position in the open files. We are also restoring current working directory. We have also implemented support for applications optimized by compiler. The compiler can optimize your single process application using technology called lightweight processes. Each lightweight process has its own registers and signals which we are storing. This is specific technology used by Solaris operating systems. We are also storing some process limits like maximum number of open files, maximum number of memory which application can use. It's easy to use our package. If you have root privileges, you can install it in standard way for Solaris operating system. And you must remember that the checkpoint and resume binaries should be globally accessible and should have proper set of rights. To checkpoint any application, you use our command. You must select the process. You must pass the process identifier to the checkpoint binaries, and this application will store all information to the default directory. To restore the application, you use resume command, and you must pass the parameter where the image is placed on the operating system. We have prepared the reference configuration for collaboration of our tools with SunGrid engine, which is the Sun's queuing systems used to run jobs in the clusters or grids. When you want to submit a job to the grid, to the SunGrid engine, you use qsub command, and you must select the checkpoint table object, which will be used for your application. You must prepare some shell script for running a process, and you must define in the SunGrid engine some queue and some checkpointing object. I have marked important changes which must be done. Based on the experience gained working on checkpointing for Solaris operating systems, we have defined the next project. It was the SGI Grid project, which was also co-founded by Polish State Committee for Research. What's interesting, the project started when the new processor's Titanium was introduced to the target, so we was working on completely new platform. We have got one server for developing purpose. It consists of 4 CPUs. On this server is working SGI Propack operating system, which is developed by SGI company. This operating system is based on Red Hat Linux, and the Silicon Graphics prepares the dedicated kernel for this machine. Because we have successfully implemented support for multiprocess application in model one parent, many children, we have decided to extend these assumptions for full tree structure in this project. So the most important features which we have developed is resource virtualization and support for multiprocess application. To guarantee the correct allocation of identifiers of resources, we have again introduced the virtualization mechanism, but this time the virtualization mechanism was implemented as the kernel module. There is also a lot of other features which we have included in our package. It is support for interactive programs, support for signals, support for program linked statically and dynamically, support for open files, and so on. What is interesting is a support for zombie process, because the multiprocess application, once again, must have emulated process which finished before their parents. So we have included this functionality in the virtualization module. As I mentioned earlier, the virtualization mechanism allows us to restore original values of kernel resources. The important, in our point of view, resources are process identifier, process group identifier, and system file keys and identifiers, which are used by System 5 interprocess communication. Our package consists of 4 files, 2 kernel modules, and 2 user-level applications which are available for the users. There are some dependencies between those packages. For example, the checkpointing application is responsible for attaching user's process and for collecting a lot of information about the process. It uses ptrace function, procfs, and our checkpointing module, which is responsible to access all the resources that make up process context. To restore, okay, I will skip this slide and I will tell you a few words about there were described some issues specific for this architecture. Right now, we are working on grid checkpointing service. It is developed as a part of the Core Grid project, which is co-founded by European Union. Our grid checkpointing service is developed as a part of work package 5 monitoring services. We have defined the grid checkpointing architectures, which we have divided into several layers. That the bottom layer, checkpoint restart functionality provider, is responsible for collaborating, executing, gathering some information, sending applications images with checkpointing services installed on the node. So we have do not precise the tools which could be used on the bottom layer. We want to make this layer as flexible as it is needed. The checkpointing restart provider interface will translate the requests from upper layer grid restart checkpointing service to specific bottom layer. So only the grid checkpointing only the checkpoint restart grid service will be used to provide checkpoint information into other grid services and other grid-enabled applications. And summary, we have, as you see, until now we have developed a few low-level checkpointing services. Now we are working on grid checkpointing services. All packages which we have developed are available for download from our website. We are supporting a wide range of high-performance computing applications, 64-bit applications. We know that there is some work to be, that there must be some work, that some work must to be done to support very wide range of applications like MPI application, multi-threaded applications. And
thank you very much. So the floor is open for questions and or comments. Okay. If not, let's thank all the three speakers of the session. So the session is closed. Thank you very much.